Hello and welcome to this session. In this session, we are going to discuss about partial ordering. A relation R on a set S is called partial order if it is reflexive, that is, A is related to A for all A belonging to S. It is antisymmetric, that is, A is related to B and B is related to A. This implies A is equal to B. It is transitive, that is, A is related to B and B is related to C, implies A is related to C. A set S together with a partially ordering R is called a partially ordered set or a poset. It is denoted by SR. Sometimes relation R is denoted by precedes or equal to symbol, and generally we denote a poset by the ordered pair set S with binary relation precedes or equal to. Let us see the following example. Less than or equal to relation on the set of integers is a partial order. We have to prove that the ordered pair Z with less than equal to is a poset. For this, we will prove that this relation is reflexive, antisymmetric and transitive. First, we prove it to be reflexive. Let A belong to Z, the set of integers, then clearly A is less than equal to A for all A belonging to Z, the set of integers. So, it is reflexive. Now we prove it to be antisymmetric. Let A and B belong to Z, the set of integers, such that A is less than equal to B and B is less than equal to A. This clearly implies that A is equal to B. So it is antisymmetric. Now lastly, we prove it to be transitive. Let A, B and C belong to Z, the set of integers, such that A is less than equal to B and B is less than equal to C. Then it clearly implies that A is less than equal to C. So it is transitive. Thus, less than or equal to relation on the set of integers is a partial order. Let us now discuss Hayes diagrams. There is a convenient graphical representation of partial orders called Hayes diagrams. Consider the digraph representation of a partial order. Since we are dealing with partial order, then we implicitly know that the relation must be reflexive and transitive. Thus, we can simplify the graph using the following. First, remove all self loops at each vertex. Second, remove all transitive edges. It is drawn so that all edges point upward eliminating arrowheads. For example, we want to construct a haze diagram for the poset set 1, 2, 3 with the binary operation less than or equal to. So here the elements of poset will be 1 less than equal to 1, 2 less than equal to 2, 3 less than equal to 3, then 1 less than equal to 2, 2 less than equal to 3, and 1 less than equal to 3. So we have the following set containing elements 1, 1, 1, 2, 2, 3, 1, 3, 2, 2, and 3, 3. Let us first see a diagram showing all loops of reflexivity and transitivity. See here, self loops at 1, 2, and 3 show reflexivity, that is 1 is less than equal to 1, 2 is less than equal to 2, and 3 is less than equal to 3. So we will remove these. Then 1 is less than equal to 2, 2 is less than equal to 3 implies 1 is less than equal to 3. So the edge joining 1 and 3 shows transitivity. So we will remove it. So we are left with the following diagram. Now again we will draw it so that all edges point upwards and will remove arrowheads showing direction. So we are left with this diagram. This is the required haze diagram. Now let us discuss maximal and minimal element. Let ordered pair S with binary relation precedes or equal to be a poset. Then an element B belonging to S is a minimal element of S if there is no element A belonging to S that satisfies A precedes or is equal to B. That is, it is not greater than any other element in S. Similarly, an element B belonging to S is a maximal element of S if there is no element A belonging to S that satisfies B precedes or equal to A, that is, it is not less than any other element in S. See, from this haze diagram, we see that 1 is the minimal element and 3 is the maximal element. So in this session, we have discussed about partial order. This completes our session. Hope you enjoyed this session.